and then maybe go over a couple of the review problems. Did you try looking at it this weekend?
Yeah, I did.
Nice. How many people actually memorized the trig derivatives? Okay, because if you didn't do that, that should be your priority, because that will just get you for points over and over and over again. So make sure you know those trig derivatives. Okay, so extra help today and tomorrow if you need it. Test Wednesday. Got it? All right. So remind me, guys, the day 22 notes. Did we do a few of those with the piecewise functions? Just the first one? Maybe we should do a couple of these then, just to make sure you're comfortable with that. So we did the first one. That's this one. Okay. And it turned out it was continuous at 2, but not differentiable. True. All right, so let's try another one of these. We're asked to determine if the function's differentiable at -1. So we got to first check if it's continuous. Let's make this. Oh, you know what? Let me do this thing. Day 22? Hang on. Yeah, we only did the first example, so we got to do a little more. Oh, people at home get to see me calibrate. That's fun. No, it's not calibrated. Sorry, kids. Nah, like sometimes it's just so insisting I have to go really full screen.
I could have done that.
It's way too complicated for us. Way too complicated. Okay, so first we got to check if it's continuous at -1. So to be continuous, what has to happen? Yeah, just. Yes. We got to find a limit. So first we're going to check out if it's continuous at x equals -1. We're going to find the limit of f of x as x approaches -1 from the left. And we're going to find the limit of f of x as x approaches -1 from the right. We're not setting them equal to each other. We don't know that they're equal. They didn't tell us it was differentiable there. They're just asking us, is it continuous? Is it differentiable? So how do we find the limit of f of x as x approaches -1 from the left? Right? So, and we're going to plug -1 into the second branch here. And what do we get when we do that? -3. Bless you, I guess. That was a sneeze. What that was. All right, what about the limit of f of x as x approaches -1 from the right? Top one. All right, let's plug -1 in there. See what we get. -1 squared plus -1 minus 3. What does that equal? -3. So does the limit of f of x as x approaches -1 exist? Sure does. It does exist. It's -3. The left and right hand limits were the same. Technically, to be continuous, not only does the limit have to exist, what else has to exist? F of -1 has to exist. Does f of -1 exist? Yeah, because this tells us that when x is equal to -1, it tells us how to get y. It's -1 squared plus -1 minus 3, which we already know what that is, right? That's -3. So the limit is -3. The functional value is -3. They're equal, right? So what do we know about the function? So since the limit of f of x as x approaches -1 equals f of -1, what do we know about the function so far? It's continuous. F is continuous at x equals -1. So that's what it takes to show a function is continuous at a particular x value. The limit's got to exist, the function has to exist, and they have to be the same. So we know it's continuous, so there is a chance it's differentiable. If we got that it was not continuous, we wouldn't even bother checking. It would be impossible to be differentiable. if it wasn't. But it is. So now we want to see if it's differentiable. So what's the first thing I got to get? The derivative. Can you guys tell me what the derivative of the first branch would be? Good. 2x plus 1. Now, because I'm not sure if the derivative exists at negative 1, I'm going to just say this is the derivative when x is greater than negative 1, because I don't know yet if the derivative exists at negative 1. That's just a little thing. You're not going to lose points for that. But what about the derivative of the second branch? Negative 1, right? And that'll be when x is less than negative 1. Now, to be differentiable, not only does it have to be continuous, which it is, but the slopes coming in from the left and from the right have to be the same so that when the pieces come together, it's smooth, there's no corner. So we have to find the limit of f prime of x. We want to see what the slope's approaching as x approaches negative 1 from the left, and see if what the limit of f prime of x is as x approaches negative 1 from the right. So what is the limit of f prime of x as x approaches negative 1 from the left? Negative 1, good. From the right, how are we going to get it? Plug it in the first one. So 2 times negative 1 plus 1. What? Okay with that? That's negative 1? Nice. So as you come in from the left, the slope's negative 1. From the right, the slope's negative 1. Is it differentiable there? Yes. So f prime of negative 1 is actually equal to negative 1. In other words, it is differentiable. F is differentiable at x equals negative 1. If we got different slopes coming in from either side, it wouldn't be differentiable. So this function is both continuous and differentiable at negative 1. Now, in these first two examples that we did, they gave us a piecewise function, and we had to determine if it was continuous, and if it was differentiable. I want to at least do one or two examples where they tell you it's differentiable, and you have to go back and solve for some unknown values. But this is very AP-ish, word. So I want to actually, this is the same thing again. I'd rather try something like this. Just a little different. Same concept, but so if you look at this example here, they say find the values of a and b that make the function differentiable. Now, they mean everywhere. What's the only value we have to worry about? 1. So the fact that they're saying find a and b that make the function differentiable, it is going to be differentiable. We just have to find a and b. The fact that it's differentiable, does that mean it's continuous or any? Yeah. That implies it's continuous. All right, so that implies it's continuous. So the fact now that we know it's got to be continuous at x equals 1, what do we know about the left and right hand limits? They have to be equal. So we just set them equal to each other. In other words, the fact it's continuous at x equals 1 means the limit as x approaches 1 exists, which means the limit of f of x as x approaches 1 from the left has to equal the limit of f of x as x approaches 1 from the right. You don't have to find them separately and see if they're equal. We know it's differentiable, we know it's continuous, so we know they are. Now, what is the limit of f of x as x approaches 1 from the left? We're going to get that. How would you get that? Yes, ma'am? Yep. Yep. So you're going to plug the 1 into the x of the second branch, because it's less than 1. It's approaching 1 from the left. So we have b times 1 minus 3, or b minus 3. That's the limit of f of x as x approaches 1 from the left. That has to equal the right-hand limit. How are we going to get that one? We're going to plug 1 into the x of the top branch. So it's going to equal a times 1 squared plus 1. Let's see, we have b minus 3 then would have to equal a plus 1. Can't do too much more. We can just get constants on one side. What do you want to do to get the constant on one side? You want to subtract 3? Yeah. I'm going to add 3. So far what we know is that b has to equal a plus 4. We know that b is 4 more than a, but we don't know what a is, so yeah, you could do b minus 8. So that's not enough to solve for a and b. We're trying to find values of a and b that make it differentiable, which means it's continuous. So we got that equation. But it's also got to be differentiable. No corners cut for vertical tangents. So just like before, when we didn't know if it was differentiable or not, we had to find the piecewise function for the derivative. Now, a is a constant, b is a constant, so what would the derivative of the first branch be? 2ax. Now, we know it is differentiable at 1, so I could keep it x is greater than or equal to 1. I don't have to worry about that. I know the derivative exists there. What about the derivative of the second branch? Just b. And that's when x is less than 1. Now, the fact that they told us it's got to be differentiable there, we know that the slopes coming from either side are going to be the same. So we don't have to just get them separately and then check if they're equal. We know they're equal. We know that the limit of f prime of x as x approaches 1 from the left has to equal the limit of f prime of x as x approaches 1 from the right. Okay, so we got the f prime of x. So what would the limit of f prime of x be as x approaches 1 from the left? So look at this one. And what is it? B, right? That has to equal the limit of f prime of x, the slope, as you come in from 1 from the right. What's that going to be? 2a, and then we're plugging 1 in for the x, so 2a times 1. Now we know b equals 2a. So in order to be continuous, we found out that b has to equal 4 more than a. We got this equation. Oh, you're thinking. See, now the fact it's differentiable also means that b has to equal 2a. 2 equations, 2 unknowns. We're solving a system of equations. What's one of the major techniques you use to solve a system of equations? Yep. Okay. So you're going to set them equal. In other words, like, what are you going to set equal to what? Tell me what you do here in the next step. I want to see if you're... Yeah. So what you're doing is, one of the techniques that we use a lot to solve a system is substitution. You solve for one of the unknowns in one equation, like it is over here, and you substitute that into, so whatever one of your variables equals in one equation, you substitute into the other equation. So we're going to replace the b over in this first equation with what b equals in this second equation. So 2a equals a plus 4. So what does a equal? 4. And once you know that a equals 4, you could go back to either equation to get b. What does b have to equal then? 8. We're okay with that? Whether you take 2 times 4, you're going to get 8, or 4 plus 4, you're going to get 8. So we just found the values of a and b that not only make this piecewise function continuous, makes it differentiable. When those pieces come together, they not only come together, they're not only continuous, but they come together with the same slope, so it's nice and smooth. Want to do one more of those? Okay. Yeah, you do. Who wouldn't? It'd be crazy. I like these. This is what they tend to give you on the AP exam, this type. Same directions here. We got to find the values of a and b that make this piecewise function differentiable, which implies it makes it continuous also. We're trying to find values of a and b that make this function differentiable, in this case at 2, because it would be differentiable everywhere else. What do we know about, what is the fact that it has to be continuous? What does that tell us? Yes, Ryan? Yeah, the left and right hand limits have to equal each other, or else the limit wouldn't exist and it wouldn't be continuous. So just knowing it has to be continuous at x equals 2, we know the limit of f of x as x approaches 2 from the left has to equal the limit of f of x as x approaches 2 from the right. Now we just got to fill in those limits. What would the limit be as x approaches 2 from the left? 2 into the x of your first branch. What do you get? 8a plus 1. Right? We plug 2 into the first branch because that's x is less than 2. Okay, that's got to equal limit of f of x as x approaches 2 from the right. What do we get for that one? b plus 10? Is it positive or negative? Well, first you put the 2 in, right? You have negative 1, but you square it. That's positive. So positive 1 times b, that's b. All right, well, we can't do too much more. What else do you want to do over here with this one? I just don't want constants on both sides. Subtract the 10? And you had a choice. I think that's a good choice, though, because then you'll know what b equals with this one. So b equals 8a. 1 minus 10 is negative 9, right? So far, we've got our one equation. We know that b is equal to 8a minus 9. Now, we're trying to find the values of a and b that make it differentiable. Right? So now that's what we know so far. Just to be continuous, that has to be true. Now, I want to make sure it's differentiable. So what should I get next? The derivative. Yes, the piecewise function for the derivative. Right. Okay. Now, I will say, though, for this second branch, yeah, let's multiply that out. What is x minus 3 squared? Yes, Cameron? 6a plus 9. So I can leave the b factored out. It's a constant multiplier, but we'll need that to write the equation, the piecewise function for the derivative. Let's take the derivative of the top branch first. The top branch, we've got ax cubed plus 1. Oh, what did I do? Oh, what am I doing? Thanks. Okay, what would the derivative of the top branch equal? Good, 3ax squared. So that's going to be the derivative when x is less than 2. Now, the second branch I wrote down here. So when we take the derivative of this, we don't need to distribute that b because it's a constant multiplier, right? We can just leave it and multiply by the derivative of bx squared minus 6x plus 9. What would the derivative of x squared minus 6x plus 9 be? 2x minus 6. So that's the derivative when x is greater than or equal to 2. It's a constant multiplier, the b, so you can, when you take the derivative, you can just leave it. If you wanted to distribute, you could. You can get the same thing. It's like the product rule with the second half dropping out. Okay, erase this part here. So, now that we've got the derivative, the piecewise function for the derivative, and we know it's differentiable at 2, what's got to be true? They got to equal each other, right? We know that the limit of f prime of x, as x approaches 2 from the left, we're doing the same thing we did over there with the function. Now we're just doing it with the f primes. Has to equal the limit of f prime of x as x approaches 2 from the right. You know I'm going to ask, what is the limit of f prime of x as x approaches 2 from the left? 3 times a times 2 squared, which would be what? 12a. 12a has to equal, what is the limit of f prime of x as x approaches 2? b times negative 2 or negative 2b? Good. Okay. Can we clean this up a little more? Divide by negative 2. All right, so we know from this one that b equals negative 6a. So that's our second equation. So the fact it was continuous gave us the equation b equals 8a minus 9. Now we know that b equals negative 6a. Can we solve? What are we going to do? Set them equal to each other, right? We're going to substitute in for 1b what it equals in the other equation. So I have 8a minus 9 has to equal negative 6b. All right. I just believed her. Oh man, I can do it. Oh, I am actually pretty well calibrated today. Okay. I know how to do it. Just put that. All right, so this is not going to work out to be an integer. That's all right. We're fine with rational numbers, right? Rational numbers are beautiful too, right? So what do we get? Let's see. What would you do next? Add 6a? Oh, let's add 6a to both sides. I like that. And at the same time, because we're multitaskers, as we added 6a to both sides, what else should we do to both sides? Add 9, right? We can do two things at once. We can handle it. So we have 14a equals 9. 9/14. Love it. So that's what a equals. A equals 9/14. Now b is equal to negative 6 times a. Okay, wait a minute. So we have negative 6 times our answer for a, which is 9/14. Now I'm going to put that over 1. No, don't touch the calculators. They'll burn you. You can do top times top, bottom times bottom, but usually if you see anything, you can simplify first. Is there anything that goes into a numerator and a denominator? 2, right? 2 goes into the negative 6, negative 3 times, into the 7, 7. Yeah, I see like that. Fine. Yeah, but now we multiply across. What do we get? Negative 27 over 7. Yeah. So you just multiply first. You had negative 54 over 14, and then you reduce. Yeah. Got to reduce sometime. Yeah. All right. So that was our answer. So we had a is equal to 9/14, and b was equal to negative 27/7. Those are the two. On the AP exam, you don't lose any points for not simplifying. But the thing is, if it was a multiple choice question and that wasn't there, you have to find it. Okay? No. 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 No, they would have. How evil do you think these people are? No. Okay. So I think these are kind of fun. Do you like them? Yeah. Yeah, they're fun. I actually like the find A and B that make it differentiable a little more. It's a little less work. You can just set them equal to each other. I thought we would today go over just a couple of the worst questions on the review sheet. What was like the worst thing you saw so far? Some people I know didn't really try that much. Oh, I should have summarized it. Oh no.
14.
Maybe we should talk about 6. Wait, let me just see what 14 is. Then we're going to go to 6. They're excited. Kids are excited. Oh, 14. Yeah, let me just show you 14. Then we're going to do 6. 14, I just want to, you have to be able to use the calculator for 2 things. To find the derivative. You don't know if so even like, I know there's some great kids in here who don't like the calculator at all. You still have to know how to use the calculator to find the derivative at a particular value. So on your home screen, you have to go to nderiv, that's math 8, put in the function, the ln of the absolute value of x, comma x, comma 5. You have the, probably the print is all different, like it says ddx and stuff on it. I'll change it for you, just so you can blend in with us. Plus CE, I never saw this one before. Mode, it is cool. I'm going to go down to where it says math print. I went to mode, and I'm going to math print. I'm going to classic. Now you can be classic with us. Now do the math 8. Oh my God, it's even thinner. It's so cool. Yeah, but it's only because it's 5. If I pick a negative number, yep. Point. You only have to be accurate to 3 places in this class, so the actual answer is 0.2. Now, and here. Now, the second part of this, actually, let me just go back to that. So when you want to find the value of the derivative at a particular value at a number, you just use nderiv, the function, comma x, comma the number. When you want to graph the derivative, you have to go to your y equals screen, then put in the nderiv, the same thing. That's it. Yeah, the only difference is, other than being in your y equals screen, you do comma x like you did before, but then you do another comma x. Instead of the number, you put in comma x, and that'll graph the derivative. No, and what it should look like is this when you graph it. I picked a zoom decimal because I love it. Yeah. Zoom decimal just means that when you hit trace, oops, I didn't mean to hit trace. You see how the x's go up by 0.1 every time? As you go up, they're not like these crazy weird numbers. The x values go up. So it's nice. You just have to sketch it. Oh yeah, all you had to do is, like, for the second part of 14 was just sketch the derivative. So sketch something that looks like that. But you gotta know how to put it, because I'm gonna give you something that you don't have a rule to differentiate. You have to know how to graph the derivative. Yeah. I want you to graph the derivative f prime of x. So, no. For the first part, you just happen to find the derivative at 5. But now I want you to graph the actual whole derivative. That is so smart. Yeah, you could do second calc, value 5. Oh, I like that. What did I do? Oh. Okay, wait, I go back to my graph. Because I think I was on the, okay, it should be okay over here. Wait. Oh, yes. That's true. I could just go like this and go make it go out to 5. Oh, all right. I'll change my window. Yeah, you're right. Zoom 6 will go out to 10. Yeah. It's just so tiny. It's hard to see. But yeah. Now you can do it. There's the point for you again. Yeah.
So if we wrote 5,
Because my graph before only went up to like, yeah, 4.7. Like, I don't know about 5. I can't see it. I can't see it in my window. Yeah. All right, now I want to talk about that second question Emily asked me about 6, which is the only really evil question on this whole review. Well, yeah. Oh, 9 is fun. You got to get the regular derivative using your quotient rule or whatever. Like just write out what it would be, and then fill in 2's or whatever for all the x's. Wait, we got to do this 6 because I feel like if we handle this today. All right, let's look at this, guys. This is you want a fun time in this class. This is it. This is it for you. All right. So we have to just get, well, the good thing is on your test on Wednesday, you don't have to simplify anything. You can leave negative exponents, you can leave fractional exponents. Just you apply the rule and you're done, okay? Wednesday, okay? But it's still, I still can't even fit this whole derivative on a line. That's how bad it is, or good it is. All right, now first of all, I know you see products and you see quotients. So you have to know how to start though. Overall, is this whole thing a quotient or is the whole thing a product? Quotient. So you have to use quotient rule. But when I get to D high, what am I going to have to use? Product rule. And when I get to D low, what am I going to have to use? Product rule. So we have 2 product rules inside of a quotient rule. That's right. What if you what? Some people like to, it worries me though. Some people start doing the product rule, and I feel like they're not going to put it together in the quotient rule. Let's do it together. Okay. So we agree it's a quotient. Look out, I'm going to start over here and I still won't finish it in one line. I'll have to continue. All right. I'll do low. You guys do D high. So we have low. Look at me go. Nice. Okay. All right. Your turn. D high. Okay. Here. Cotan x. All right, I just want to put a little arrow to this and write it as 7x to the 3 over 2. Okay. Because there's an invisible 2 here. When you don't see a root, it's a 2. All right, so here we go. So first times derivative of the second. So cosine x plus, no, we're still doing the whole behind. First, plus 21 over 2x to the, well, I'm just going to leave 1 over 2. I'm not even trying. All right, so right now we're in the middle of D high. We've got the low, and we're starting D high. We have first times derivative of the second, plus the second, bunch of quitters, times the derivative of the first. What? You didn't memorize those yet. Uh-oh, we're in trouble. Negative cosecant squared x. Now, do we have the whole numerator of quotient rule? We've got our low, and we've got D high. That's it. So we got to keep going. So on the same line, we have minus less. All right. See where? This is a quotient. So we have low. That's right here. D high, we had to use the product rule. That's why it's a big old The where? The radical what? Yeah, we took the derivative of the first. We had we had low, d high, where we have first times derivative of the second. This is where we took the derivative of that. Plus the second times okay, so less high. So cotan of x, sine of x plus 7 rad x cubed. D low. Okay, so for d low, though, you're not going to just start taking the derivative of each one separately, are you? What are you using? Product rule. Okay, now, square root of x, that's x to the half, all right? So let's take the derivative of secant x times x to the half. So first, secant x times the derivative of the second. That's right. Plus the second, I don't care if you call it x to the half or square root of x, I don't know. Times the derivative of the first. Secant x, tan x. What are you thinking? So far we have low d high, less, this is your high. Oh no, this is on the test. This is a 10-pointer. Yeah, this is a fun one to grade, let me tell you. All over. Yeah, one like this. I do lie a lot, but this time I'm not. Okay, what I would suggest to you when you have a problem like this is set it up for yourself. Like just when you're looking at this, I mean, I would set it up so you don't forget. Like I would write down cotan x. I would have left, low, for the d high, I think I would have left some big parentheses open. A little plus in the middle, because you know it's product rule. No, you leave it. Don't even try to, because it'll be painful. No. Yeah, that would be nice. Come on, this is fun. And I get. Yeah, when your heart rate starts to come down, and the vision clears. Yeah. I just wanted to say, guys, it's not always so ugly. Do you think this one? You know, guys, you could look at this as product rule, where the first is a quotient and the second is a product, but you don't have to. But tonight, when you're doing this, simplify it first. And this could be a one little quotient rule or one little product rule. Think about that. If you simplify before you differentiate, I know this class is way too fast, right? All right, so you know what you got to do tonight. You got to work on this. I'll give you the solutions tomorrow. Oh, it was supposed to be. I mean, if you want the solutions and you're not going to share them with anyone, I'll give them to you now. You do? Yeah, I just want people to try it first. You promised me you tried it? Yep.
For number 6, we didn't have to simplify?
No, you don't simplify anything on this. Yeah, so it's easy. Oh, I have to turn this off.